So it's been a little while since we did a derivative that looks like this. So remember that what's unique about this one, and makes us have to think about how we approach it, is the fact that we have our variable both in the base and the exponent of our original problem, which tells us that we're going to have to be able to find this derivative by using logarithmic differentiation. In other words, start by taking the natural logarithm of both sides of this equation. Because the entire reason why we take the natural log of both sides is because when we have the x both in the base and the exponent, we can't just work with it from that form, but by writing it as a logarithm, I can take that exponent and I can pull it outside of the logarithm. Because now we got rid of the x in both the base and the exponent. Now it's into a more familiar form where we can actually find the derivative of it. And so when you're finding the derivative on the right-hand side there, remember, you are going to be using product rule because this is 4x cubed times the natural log of x. And so we do original times derivative plus derivative times original. And then it's just a matter of cleaning it up as we go. And so I went ahead and did the 1 over y times y prime on the left side. And on the right side, really what I was able to do there was just to multiply the 4x cubed times the 1 over x, and I'll be able to cancel out x's. All right, now that I'm here, I still want to get y prime by itself, so I'm going to go ahead and multiply both sides by y. And then once we've done that, remember, we don't want to leave it in this form, because right now it's y prime equals something both in terms of y and x, and while technically correct, we can simplify it a lot more because we know what y equals. Remember, y is equal to the 4, or x to the power of 4x cubed. And so I'm going to replace the y in this last line with that. And so we would end up with something then that is all in terms of x, and only in terms of x, which is then a lot easier to work with. Now you might be wondering, can we clean this up anymore? If you wanted to, you could actually factor a 4x squared out of both of the terms. And so you could do a little bit of manipulation like that, but you don't need to. And after having refreshed our memory with that last one, I'm hoping that this one is going a little bit smoother. You should already notice here at the very start of it, the really telling fact is the fact that we have x in both our base and in our exponent, so I am going to have to use logarithmic differentiation as my technique, which means, yes, you will have to take the natural log of both sides of this equation to start with. All right, so now we've taken the natural log of both sides. Now we can go ahead and find the derivative. And so when we take the derivative, the natural log of y gives us the y prime over y. And then on the right side, when we find the derivative, we have to use the product rule again. So it's going to be original times the derivative, and the derivative of natural log of sine x, it's going to be 1 over sine x times cosine of x. For whatever reason, it can be very easy on this type of problem to forget about the cosine of x there. But we do need to use it because, again, it's chain rule. The sine of x is inside of the natural logarithm, so we're having to use chain rule there. All right, and then plus, because remember, I only did the first part of product rule so far. Now, derivative times original. So 1 over x times natural log of sine x. And so in terms of making this a little bit neater, there's a couple things we can do. And I'm going to go ahead and do a couple of them at the same time because we are getting a little bit more comfortable with it. I'm going to go ahead and multiply that y to both sides. So I know I'm going to end up with y times all of this exactly as it was, except I can go ahead and simplify a couple things there. So I'm going to do that. So like I got natural log of x times, well, it's going to be times 1 over sine times cosine. What does 1 over sine times cosine equal? Well, that'd be the same as cosine over sine. And what does cosine over sine equal? Cotangent. And so this would be cotangent of x there. So notice, this became the cotangent. All right, and then from there, there's not really much I can do with the second part except maybe write it as one big old fraction. So I'll make that into the natural log of sine x all over x. And then that's certainly a lot better, although we can go at least one step further and should go one step further, and that is we need to replace y with what y equals. So in this case then, instead of writing y, we're going to write the sine of x to the power of the natural log of x. That's the original y, and then that's going to be times the exact same thing that we have in the line above, the natural log times cotangent plus the natural log of sine all over x. That then is done. Right, now, I wanted to bring these questions back because we first introduced them last week and they were tricky for some of us, especially the little details. We missed certain little things, especially like this cosine often got lost in the shuffle, some things like that. We do need to be able to remember all those little details along the way though. So we're going to need to keep practicing this logarithmic differentiation as a technique, but it's not the only thing we're practicing today. I also want to take a look at practicing the kind of stuff we've been doing earlier this week as well. So here's a similar problem to the type that we were doing earlier this week. It's not exactly the same, slightly different description, and definitely a different equation. I'd like you to please try to figure out here, when is this object speeding up and when is it slowing down? Now, as you're taking a look through this problem and trying to get started on it, the first thing that you'd be trying to figure out on doing this one is we're going to need to be able to figure out both velocities and accelerations. Because remember that in order to know speeding up and slowing down, we need to know where the velocity and acceleration both have the same signs. So that means finding a velocity equation and an acceleration equation and figuring out when they're all zeros as well. All right, so first thing we'd do then is we'd figure out what is our velocity equation. So we'd be therefore taking the derivative of the original. So we'd have negative 6t squared plus 48t minus 90. Remember, the derivative of 12 is 0, so that just goes away. All right, so now we'd want to figure out what makes that equal 0. And so if I'm going to solve that for 0, figure out when the velocity is 0, I'm going to probably want to try factoring this. It's going to be a lot better than trying to do like quadratic formula on it or something ugly like that. So notice I can go ahead and factor out that negative 6 as a first step. That's going to make our lives a whole lot easier. And then, yes, it is factorable from there. So you end up with t minus 3 and t minus 5. And so the velocity is 0 at 3 and 5. We want to repeat the same process for the acceleration. So first thing is we figure out what the acceleration equation actually is. So that's the derivative of my velocity. Now I've got some options about what I use for velocity here. I could use that form of the equation, that form, or that form. But here I'm going to be using product rule, which I don't really want to goof around with. I'm just going to do the derivative from that form. There's nothing magical about it. I just think it's going to be a little easier. So that would give me negative 12t plus 48. And then again, I'm going to try to be figuring out when does the acceleration equal 0. So we go 0 equals the negative 12t plus 48 and solve it. So I'm going to move the 48 to the other side. Then I can divide both sides by negative 12, and we end up getting that t equals 4. Now, if you're then unsure about where to go from here, once we've found these values, the next thing that we're going to be doing together here, but I'm going to give you some time to do it yourself first, is I'm going to be drawing out a line like this. And I'm going to be marking out on this line those critical points that we really care about, so that I can then figure out for each of them, is the velocity positive or negative, and is the acceleration positive or negative for every single one of those intervals. All right, so now we want to pull that information together and actually use it. So we are going to set up a line, and in this case, we actually know where the endpoints of this particular line are going to be. It's not negative infinity to infinity in this particular case. Some of you were wondering, what's it matter that we're looking at the first 12 seconds? What's that change about it? The only thing that it changes is that when I set up my number line, I'm going from 0 to 12, not negative infinity to infinity. All right, and then from there, remember my zeros were at 3, 5, and 4. Those are the numbers I need to then kind of tick out on my diagram here. So I've got 3, 4, and 5. No, they're not perfectly spaced here. Is that going to change anything? No, because all I care about is just knowing for each of these intervals, is my velocity positive or negative, and is my acceleration positive or negative. And so we're going to be doing that for every single one of these intervals going down the line. All right, now in order to figure that out, I got a couple options. One way that I could figure that out is I could find a number between 0 and 3, like 1. I don't want to use 0 or 3 though. I got to use a number between them. So I might try 1, and I could plug that in to my velocity equation, and I could then figure out is that positive or negative. And then I could plug it into my acceleration equation to figure out if that's positive or negative. And then I could go to the next one, and I could grab a number between 3 and 4, which is going to have to be a decimal, like 3.5 or something like that, which I really don't feel like dealing with. So I figured there's an easier way to do this. I'm going to look at the graphs and let those tell me. So if I make a quick sketch of my graph here for the velocity, it's a negative quadratic, and so I know it's going to be looking something like that. And I already know that it crosses 0 here at 3 and 5, because that's what I found earlier up here. And so based just on looking at that graph, I can now tell that my velocity is negative to the left of 3, because it's below the x-axis over here, hence the velocity is negative. So velocity is negative to the left of 3, but then between 3 and 5, it's above the x-axis, so it's positive. So positive, positive, and then after 5, to the right of 5, it's gone negative again. To me, that was a lot faster than having to plug in 4 separate numbers and checking each. Either way works. I just think that's probably a bit easier. All right, so I'm going to do the same thing for the acceleration. Rather than having to plug in 4 separate numbers, I'm going to make a quick sketch of that graph, and I can see that it is going to be a line, and it's got a negative slope, so it's going to be looking like that. And I know where it crosses the x-axis because that's what I found up here. I found out where the acceleration was 0 at 4. So I know to the left of 4 the acceleration is positive because it's above the x-axis. So the acceleration is positive and positive until I hit 4, and then after 4 it's negative and negative. On a case like this where we're just dealing with some fairly simple polynomial stuff where I can just look at it and know the graph, that's my preferred method. Usually I'll resort to plugging the numbers in when I actually have to go and figure out something where it's not a clear graph, not something I can just sketch quickly and accurately off the top of my head. But remember, yes, you can plug them back in to get them. If you are plugging them back in, like let's say you want to know if the acceleration is positive or negative, if you want to know what the acceleration is, plug it into the acceleration equation. It seems like a simple idea, but this is the part that gets us confused because there's so many equations floating around. Always think about what you want to get out of it, and that will tell you which one you want to put it into. All right, last step here, we still haven't answered the question. We still need to say when is it speeding up and when is it slowing down. So it's speeding up any place where the signs are the same. So that means it's speeding up from 3 to 4 and from 5 to 12. And then we shift over and we do the slowing down. For slowing down then, that's going to be any place where the signs are different. So that's going to be from 0 to 3 and then again from 4 to 5. That is our final answer. That is now done. Now, of course, as you're starting this one out, if you're feeling a little bit unsure about how to approach it, you'd be looking at your notes. And your notes will be helping to tell the story, but I also want to help you visualize what's happening here. So, like, if I was looking at a graph of this, I'd end up seeing a graph that's looking something like this. And what I'm interested in here is the total distance traveled, which means that it first was going from the start to this point, where it was traveling forward. And so I'd need to know how far did it travel during that time. Then I need to know, okay, how far did it travel between there and the next time it changed direction? Because all through here is traveling in the negative direction. So I need to know how far in the negative direction did it go. And then it turns back to the positive direction, and it keeps traveling in the positive direction until the end of our given interval. So the question is, how far did it travel in each of those intervals in order to then use that information to find out how far did it travel total. So then from there, I would need to know where those intervals are divided up. Well, notice that the divisions happen at 4 different places. The first one and the last one, those are the endpoints of my interval. What is the left endpoint of this interval? 0, which you might have figured out just by assuming. What's the right endpoint? 12. This is where that 12 comes in. The fact that it says during the first 12 seconds is basically a shorthand way of saying on the time interval from 0 to 12. All right, so then we need to know where those in-between ones are. Well, what do you notice about this one? Notice it's hitting right where it's at the top. And at the top is where the derivative is 0. It's just in this case, what do we call the derivative? Yeah, it's velocity. And so it's where the velocity equals 0. And the same thing down here. This is also where the velocity equals 0. Thankfully, we already found those numbers, right? We did those in the last problem. And if you hadn't already done it, well, then you could do it again. But we found earlier that the velocity equals 0 at 3 and 5. So those are our 4 intervals. We need to know how far did it travel between 0 and 3, then 3 and 5, and then 5 and 12. All right, now based on that, we need to know how far it travels in each of these, so we need to know what its position is at each of those endpoints. So you're going to have to figure out what is S of 0, S of 3, S of 5, and S of 12. Notice they are all the S values. I'm plugging them back into the position because I want to know what its position is at each of those times. I don't care how fast it's going at each of those times. I only care about where it was at each of those times. All right, so when we plug those numbers back into the original position equation, we end up getting these as our positions. Now, knowing those as our positions, I still need to figure out the distance traveled on each interval. So we're going to need to know, on the interval from 0 to 3, how far did it go? And then, again, from 3 to 5, remember we had 4 of these intervals, or 3 intervals rather, and then 5 to 12. There we go. And so figure out, what was the total distance traveled over each of those now? And so if you do that work, you're basically subtracting. So like I'm doing 12 minus the 96, or 12 minus the negative 96 rather. That gives me 108. Then I do negative 96 minus the negative 88, which, by the way, if you do it that way, you might say, yeah, but that gives me negative 8. Yes, it does, but since we're looking at how far it traveled during that time, we don't care how far it traveled in that particular direction. We just care how far it traveled total. So I'm just taking the absolute values of my answers as I go. If you put them in as negative as you're putting them down, that's fine, but you'll have to take the absolute values of each when you add them up. Because that's the next thing you're going to do, is go ahead and now add those 3 distances up to figure out the total distance traveled over the entire course of this object's path. When we add them up, we end up getting 1,096 centimeters as our final answer.